Welcome to the video podcast here at Ontario High School that has to do with the use of BCA tables in the solving process for limiting reactant problems. So this is more stoichiometry, a little bit beyond what our first podcast went into, so stay tuned. Let's take a look at a problem. Any stoichiometry problem, the first thing that needs to be done is to ensure that the chemical reaction equation is balanced. And we're going to work with hydrogen sulfide gas, smells like rotten eggs, burns in air to produce sulfur dioxide and water. So how many grams of SO2 and H2O are produced from the reaction of 19.8 grams of H2S with 27 grams of O2? And so our reaction equation is H2S plus O2 yields SO2 plus H2O. If you would pause the podcast and go ahead and balance that, and then we'll move on. Let's go ahead and check the balancing process. Here we have 2 H2S plus 3 O2 yields 2 SO2 plus 2 H2O. We're now ready to move on to the second step. Our next step was to set up a BCA table. Remember that B stands for before the reaction occurs. What do you have? C represents the change as a result of the chemical reaction, and A is after the reaction is complete. What amounts of reactants and products do you have? So the first thing we want to do is take the grams of H2S and the grams of O2 and change them to moles, because if you remember, we only put mole quantities into a BCA table. So I show both conversions here, the 19.8 grams of H2S times the conversion factor of 1 mole of H2S over 34 grams of H2S. So we start with 0.582 moles of H2S. And then for our O2, 27 grams of O2 times 1 mole of O2 over 32 grams of O2, which gives us 0.844 moles of O2. We put those into the before line. And before the reaction occurs, we have 0 moles of SO2 and 0 moles of H2O. Since we've been given starting amounts of both reactants, this is a limiting reactant problem, and we need to determine what the limiting reactant is. And again, the limiting reactant is the reactant that you're going to run out of first in this reaction. The reaction is going to stop as soon as all of the limiting reactant is used up. And there are several ways to find the limiting reactant. I'm going to show you the way that I prefer. It is pretty simple. And so what I will do is take the starting amount of H2S and multiply it by the mole ratio of O2 to H2S to see how many moles of O2 I need in order to have this reaction completely react the H2S. So I do that, 0.582 moles of H2S times the mole ratio of 3 moles of O2 over 2 moles of H2S. I find that I need 0.873 moles of O2 to completely react the 0.582 moles of H2S. And when I look at my BCA table, I only have 0.844 moles of O2 available, so I don't have enough O2 to completely react the H2S. Since more moles of O2 are required than are available, 0.844 is less than 0.873, the O2 is the limiting reactant because it runs out before all the H2S is reacted. All future calculations in this problem to find theoretical yield have to use my O2 amount as the starting place, because that's what's going to determine how much of the H2S I use. It will also determine how much SO2 and H2O can be made theoretically. This bears a reiteration. Since more moles of O2 are required than what you have available in this reaction, again, 0.844 moles that we have in this reaction are less than the 0.873 moles that we need. The O2 is the limiting reactant. It runs out before all the H2S is reacted. All the change values for the other reactants and products must be calculated using the moles of the limiting reactant, O2, as the beginning amount. Our next step, step 3, is to use the mole ratios to calculate the values in the change line. So here you have the three calculations that go with this, each starting with the 0.844 moles of O2. So we use the mole ratio to find out how much of the H2S we're going to use, and you'll see it's 0.563 moles of H2S. The mole ratio also to find H2O, and because H2O and H2S have the same coefficient, because they are 1-to-1, whatever the H2S changes by is also what the H2O and the SO2 will change by. But I want to show you the complete calculation, because unless you're comfortable with that relationship, you want to go ahead and just calculate it out the long way to make sure that you know what you're doing and feel comfortable with it. So showing each of these calculations, starting with the O2 and using the mole ratios to change to the SO2 formed, the H2O formed, and the H2S used. Now, in the change line, the reactants will always have a negative sign in front because we're using reactant up. The products will always have a positive sign because we're adding product as the reaction proceeds. So for our change line, for the H2S, we have minus 0.563 moles. We're going to use all the O2 minus 0.844 moles, and then for SO2 and H2O, each of those will increase by 0.563 moles. Step 4, we're just going to calculate the values in the after line, and what we'll do is we'll take the before values, and for the reactants we're going to subtract the change values from the before values. So when we do that, for the H2S it's 0.582 moles minus 0.563 moles. So when this reaction ends, we'll have 0.019 moles of H2S left. We have to assume in this problem, because we're not told otherwise, that all of our limiting reactant is used up. So the 0.844 moles we started with minus the change of 0.844 moles of O2 being used up leaves us with 0 amount of oxygen left. For the SO2, we started with 0, but we're going to add 0.563 moles, so we have at the end 0.563 moles of SO2. And for the H2O, it's the same. We have 0.563 moles of H2O when we're done. So that fills in our BCA table, and we're ready to move on to the next step. The problem asks us to find the grams of SO2 and H2O, and that's what we're going to do here. And many limiting reactant problems will also ask you to find the amount of leftover reactant. So we'll go ahead and do that as well. The beauty of the BCA table is we have all the information we need on each of the reactants and products, and so it's very easy to convert moles of each to grams of each. So to find grams of the SO2, we take our 0.563 moles of SO2 and multiply it times the conversion factor of 64 grams of SO2, its molar mass, over 1 mole of SO2, and we get 36.0 grams of SO2 formed. For water, we take our 0.563 moles of water times the molar mass of water, which is 18 grams, over 1 mole of water, which gives us 10.1 grams of H2O. Our leftover H2S is equal to 0.019 moles of H2S times the molar mass of H2S, 34 grams of H2S over 1 mole of H2S. So we have 0.646 grams of H2S left over. So very easy transition using the BCA table to find not only the amounts of each of the reactants, but the amounts of each of the products, but also the amount of the leftover reactant. Well, time for you to do a problem and see how you're doing with limiting reactant concepts. So our problem is this: aluminum chloride, AlCl3, can be made by the reaction of aluminum with chlorine according to the following equation. I've balanced it for you. 2Al plus 3Cl2 will yield 2AlCl3. What is the limiting reactant if 30 grams of aluminum and 50 grams of chlorine are used? And how many grams of aluminum chloride can theoretically form? So this is the problem. What I'd like you to do is to pause the podcast here and go ahead and solve the problem using a BCA table like we've done before. And then when you're ready, you've found all the values that you need to find. And in this, I would encourage you to go ahead and find the amount of the excess reactant, the one that is not limiting, that you find the amount of that that's left over as well. So pause the podcast, do the problem, and when you're ready to see the solution, resume the podcast. Good luck. Welcome back. Let's see how you did. I'm going to show you the BCA table here. I write the chemical equation, and I put the amounts of the reactants that I have in grams above the formula for the reactant in the equation. And then I need to convert each of those gram amounts to moles, and so I show you the two conversions here from grams to moles. 30 grams of aluminum times 1 mole of aluminum over the molar mass of 26.98 grams of aluminum means I'm starting with 1.11 moles of aluminum, and then 50 grams of Cl2 times 1 mole of Cl2 divided by its molar mass of 70.91 grams of Cl2 gives me 0.705 moles of Cl2. So I fill in the before line. I have 0 AlCl3 to start, and I'm ready to continue on. My next step is to find the limiting reactant. So I take my starting amount of aluminum. I usually go left to right just because we read left to right. So I'll start with my 1.11 moles of aluminum. I want to find out how much chlorine will completely react that 1.11 moles of aluminum. So I multiply it by the mole ratio from the balanced equation, 3 moles of Cl2 over 2 moles of Al. And what I find is that I need 1.66 moles of Cl2 to completely react the amount of aluminum, 1.11 moles, that I have. Since I only have 0.705 moles of chlorine, I don't have near enough. So I'm going to run out of chlorine before I've reacted all the aluminum. So Cl2 is my limiting reactant. I'm now going to use the amount of limiting reactant I have to find the amounts of the change of each reactant and product in the chemical reaction and fill out the change line. So my 0.705 moles of Cl2 times 2 moles of aluminum over 3 moles of Cl2, I find that I will react 0.47 moles of aluminum. So in the change line, I'm going to put minus 0.470 moles of aluminum in the change line. I have to assume I'm going to use all of the chlorine, so my value in the change line there is minus 0.705 moles. And then also my 0.705 moles of Cl2 times 2 moles of aluminum chloride AlCl3 over 3 moles of Cl2 means that I'll form 0.47 moles of AlCl3 in this. Again, you'll notice that the AlCl3 increases by the same amount that the Al decreases because they have the same coefficient. And that's just a relationship. If you can see that visually, it'll save you some time calculating. But until you can see that visually and grasp that, keep doing the calculations to ensure that you're as precise as possible in how you fill out the change line. We also want to, since we have the change line filled out, go ahead and calculate our final amounts in the after line. So for aluminum, we take 1.11 moles, our starting amount, minus the 0.470 moles that get used up, and we'll have 0.64 moles of aluminum left over. For Cl2, obviously we'll have 0 left over, and for the AlCl3, we started with 0, but we added 0.470 moles, so after the reaction is done, we'll have 0.470 moles of aluminum chloride. Now it's time to find the grams of aluminum chloride produced and the grams of aluminum left over by converting the mole quantities from the after line to grams. So 0.64 moles of aluminum left over times 26.98 grams of aluminum for every 1 mole of aluminum gives us 17.3 grams of aluminum left over. Our 0.470 moles of aluminum chloride times the mass of aluminum chloride, 133.34 grams, over 1 mole of aluminum chloride give us 62.7 grams of aluminum chloride produced. How'd you do? If you were unable to get the same answers as me, what I would recommend is that you go back, re-watch the podcast, and start over on a new sheet of paper and see if you can come to this conclusion with the correct calculations and reasoning. I wish you well, and that's how life is. Well, we've come to the end of part 2 of the video podcast series here at Ontario High School having to do with stoichiometry. We dealt specifically with limiting reactants in this one. There are several more parts to come. We need to deal with how gases behave stoichiometrically as well as aqueous solutions. So we'll get into that as we go further. And also we'll be comparing actual and theoretical yields and finding percent yield. So this is the end of part 2. I want to leave you with a quote from the eminent Greek philosopher Socrates: "Beware the barrenness of a busy life." I wish you well.